So there are several ways of looking at a physical crystal, um, apart from the one we have already discussed in the previous two modules. And one such way of looking at crystal is called as atomic close packing. So in this module, we would like to have a look at what is meant by atomic close packing, because it um, kind of let us know why certain crystalline lattices are preferred in nature than others. So before I start with the discussion of close packing, let me ask this question, uh, that why solids are formed at the first place. So this is a question we have already asked, and the answer is that simply because you lower the energy of a system. So if you have an ensemble of atoms, they lower their energy if they form a solid. Then the next question is, which kind of crystalline configuration will have lower energies than others? So uh, lower energy would mean there would be more stable atoms, or there would be more stable solids, or there would be stronger solids, or their binding energy would be larger. And a naive answer can be those atomic configurations or those crystalline structures which pack more and more atoms in the same volume, they would be more stable, because the more atoms you have, or the more atoms packed inside the same volume, means more bonds, and more bonds mean that they lower the energy or lower energy. So that's kind of a naive motivation for atomic close packing. So what does a close packing scheme does is treat atoms as rigid spheres of definite radii, uh, packed together and held together by interatomic forces, and those interatomic forces are the bonds by which the solids are formed, which can be ionic, covalent, or metallic, depending on the nature of the solid itself. Why we take atom as a rigid sphere is, I mean, kind of obvious, that you have core shell electrons by surrounded by valence electrons, and um, that kind of electronic cloud of a certain atom, they make a hard sphere, because it doesn't allow other neighboring atoms to penetrate its electronic shells. So that's kind of a valid argument to represent atoms as rigid spheres. So how would we go about representing a close packing scheme? So this is the picture we've been looking at. So it's a square lattice, so with lattice points. If these lattice points are atoms, then it's a physical crystal. To go to the close packing scheme, what we do is we expand these lattice points into spheres, and we expand it until they start touching each other, and that would be kind of the distance at which they would further they won't squeeze each other further together. So by this you can find the radius, which would be the radius of the hard sphere of an atom, and this would represent twice the radius would represent the equilibrium distance between two atoms when they form a solid. Uh, so but the in view of what we asked previously, how can we have more stable solid? And the answer was that if we have more dense packing. So if we have dense packing, it would mean that we have a stronger solid. And how can we achieve dense spacing is if we have the space between atoms, which are like here, is minimized. So how can we achieve that? So what we do is we take these hard sphere and then we shuffle around them until the spaces between and the atoms are minimized. So this is a cubic configuration which you are seeing here, and if you rearrange the same number of atoms in a slightly different way, you can see that the interatomic spaces, which were larger here, has been reduced by such a configuration, and so it would mean it is a more dense packing as compared to a simple cubic arrangement. So such a solid would be much stable solid as compared to such a solid. If you can see that this dense configuration has a hexagonal arrangement, so form a hexagon, or if you look a smaller scale, it makes a trigon. So uh, which means that the hexagonal arrangement is a more stable arrangement than a cubic arrangement, and indeed it's a true depiction of nature as well, because in nature most of the crystal are in hexagon configuration rather than a cubic configuration. But this is 2D picture. Let's go to into 3-dimensional picture. So in the previous slide, we looked at a 2-dimensional picture of closed packed atoms, and we found out that if you have a hexagon-like arrangement of atoms in 2 dimension, you get dense packing. So the hexagon has been shaded gray here just for better illustration. Now the next question is where can we place the next layer of atoms on top of them to build a 3-dimensional crystal? And the natural answer would be we can place atoms on the at the gaps between these atoms. So naturally they would either another layer would go into would be placed either on this gap or either on this gap. So these gaps are labeled A, B and C depending on their orientation. So you can have B, B, B gap or C, C, C gap. So in total you have 6 gaps on which atoms can be placed on top of the first layer. So let's place it like this, the second layer on top of this, the first layer, and these atoms have been placed on this B gaps which have been labeled B before. So you can see that the C gaps are left unfilled. So all these, the second layer atoms, they are placed on top of this B gap. This is, so we have formed a 2-layer atoms. What about the third layer? And that's where it's interesting that 2 things can occur. So if you look at this arrangement, the 2 layers, you have gaps. You have a gap here or you have a gap here. So either you can put your atoms on the C's or you can put your atoms on the A gaps. If the third layer of atom they are on the A gap, so they would be exactly on top of the A layer atoms, and if they are put in the C gaps, then they would be not on top of the A but rather between B and A atoms, that is the C gap. So you can have so the first layer is A, the second is B. If it is A, this is called as HCP arrangement. If the first layer is A, the second is B, and then the third is C, then it is called as a CCP or an FCC arrangement. So these you do have these 2 order, an AB arrangement, which would represent hexagonal close packing, and ABC, which would represent a face-centered cubic. So these 2 configurations are the close packed 3-dimensional crystalline arrangement, and indeed it is true that in nature most of these elements, they either crystallize into a hexagonal crystal arrangement or an FCC arrangement. Just to give you an idea, 33 elements of the periodic table, they crystallize into an HCP structure. So to have a better understanding of the difference between these 2 close packing systems, let's first look at the hexagonal close packing. If you look at the hexagonal close packing from a different angle, it looks something like this. So you have your first layer which form a hexagon given by this, and then you have these gaps, so that the second layer of atom, which is the B atom, they sit inside these gaps, and the third layer which sits on top of the second layer, such that these atoms exactly are on top of the first layer. That's why this is an AB arrangement or ABA arrangement. So this close packing, you can look it in the usual lattice picture is something like this, which is the hexagonal close packed arrangement. So you have your hexagon unit cell, and then you have these 3 atoms. So if you compare it with the hexagon primitive unit cell, The hexagon primitive unit cell looks like this. So you have hexagons forming the lattice points, and that's your whole unit cell. The big unit cell, within the unit cell, the big unit cell, you have the smaller unit cell. The difference between the close packing and the Bravais lattice, the Bravais hexagonal uh, unit cell we defined earlier in the last module, is these three extra atoms which are here in the close packing system but are absent in the Bravais lattice. So in other words, the hexagonal close packing arrangement is not a Bravais lattice. The other close pack system was the ABC arrangement, which we call as the FCC close pack arrangement, which has an A layer of atom, and then um it has B layer on top, and then C layer, and then A layer again. So the A and this A are exactly, these atoms are exactly on top of each, in the same line. So, how is such a structure, such a combination, or such a close pack arrangement is an face-centered cubic arrangement? To see this, you have to look at a slightly different view. So, if you look at such a view of the ABC close packing, you can identify a unit cell such that this unit cell is exactly like a conventional unit cell of an FCC lattice. That's why this configuration is called as an FCC lattice. So this is just another view of looking at FCC crystal in a big picture. To describe the hexagonal close packing, uh, there are two unit cells which you can identify. You can have this super unit cell which consists of this whole hexagon, or you can identify three different unit cells within. So these unit cells are marked in yellow, green, and blue. Um, each of this unit cell contains uh, two lattice points. So in general, this whole big hexagonal unit cell, it will contain six lattice points. Let's have a look at just one of the smaller unit cell, which is represented here. You have these edge atoms, and you have this one atom which is in the center, not in the center, but placed entirely inside the unit cell. So these edge atoms make one lattice point, and you have this other lattice point fully enclosed. So this unit cell is formed of two lattice points, and similar for this this unit cell and this unit cell. So in total, you would have 6 unit cell. Just to reiterate again, if you compare this with your Bravais hexagonal unit cell, the center atoms are missing in this one, so it's not a Bravais lattice. You can make the hexagonal close packing unit cell a Bravais unit cell by the following procedure. So let's consider the usual Bravais hexagonal unit cell, the big unit cell, and identify the lattice vector, the primitive lattice vector in XYZ coordinate system, so as defined here. So these three, A1, A2, A3, would represent your primitive lattice vectors for this unit cell, and you can describe them in terms of the X, Y, and Z coordinate like this. This A1, the magnitude of A1 and A2 is exactly the same, but A3 has a different magnitude as compared to the other two primitive unit vectors. So this is the hexagonal unit cell, the full hexagonal unit cell for the close packed system. And as we said earlier, that it has an extra atom. If we take a unit cell out of this, then it contains an extra atom, and the location of that atom is such that if you move along A1 by 2 by 3 distance, and along A2 by 1/3, and along A3 by a half, you would reach the location of this atom. So to form the close packing system, you can superimpose the bases on your Bravais hexagonal primitive unit cell. So the lattice is a hexagonal primitive, and the basis atom is such that you place an atom at 0 0 0, which would be at the lattice point, plus another one at this coordinate system, which would give you this extra atom. So by combining a hexagonal primitive unit cell, which is a brevet, with the basis like this, you can reconstruct your hexagonal close packing system. So close packing is just another tool for analyzing crystals, and you can analyze any system using close packing arrangement. So this is a cubic system with a primitive body-centered and face-centered cubic system. And in close packing, what happened that you enlarge these lattice points until they meet each other in either of these cases. So you get your close packed simple cubic, body-centered cubic, and face-centered cubic system. So you might see here immediately that this close packing uh, tells you some other aspect, some aspect of crystal which you haven't discussed before, and that is how how large are the gaps in these crystals. And as you can see, this is completely empty in the middle. This one has gaps here and on the faces, and this one seems to be the most close packed system. That's why FCC, or face centered cubic, is one of the close packing system, the densely close packing system within the crystal systems. So to find out how efficient the packing is, you can actually measure the packing efficiency using this atomic close packing. So the packing efficiency is a parameter which you can actually measure for a certain crystalline system, and it's given by the volume occupied by atoms within a unit cell divided by the volume of the unit cell itself. So let's take a BCC crystal with a lattice point in the center and the one at the edges or at the corners. So you can cut a plane diagonally across this BCC. So if you let's say imagine a plane which starts from here and it cuts through in the middle until it reaches the other edge of this. So that's how it would look like. And if you look straight in here, you would see one full atom in the middle and then quarter atom each in the at the edges. So what would be the packing efficiency of such BCC crystal? So first we have to find the in the close packing, what is the radius of this close packing arrangement. So these two to find that, you have to find what are the length of these sides. So these two sides have a length of a, which is the length of conventional unit cell. This would be under root 2a because a diagonal across the BCC, and this is a. So you can find this the distance from this edge to this edge, which is basically 4 times the radius of the spheres. So you have one radii here, 2 radii here, and another here. So 4 times. So and r, this radius is important because this is the radius of the close packing, and from this you can find what volume of the unit cell is occupied by the atom and what volume is not occupied by the atom. So this 4r is basically given by this distance, and this distance you can find by these two distances, which would be basically under root 3a, and from here you find the radius of the sphere it's themselves in terms of a, where a is the length of the conventional unit cell. You can find the packing efficiency by finding the volume of atoms. So the volume of one atom would be given by 4 by 3 pi r cube, and since you have two such full atoms in a BCC unit cell, a conventional unit cell, you multiply it by 2. So 2 multiplied by 4 by 3 pi r cube would be the volume occupied by the atom within a unit cell, divided by a cube, where a cube is the volume of the unit cell itself. So you put the value of r in there, and you get a certain value. A cube cuts, so you get a specific number, and that number is actually the packing efficiency, which in this case is 68%. So which means that 68% of the volume of a BCC is occupied by the units, by the atom or the lattice points, using atomic packing arrangement. um, you can also look at this plane which we cut out of this unit cell, and try to find out how much area of this plane within the unit cell is occupied by such a formula. Just try it yourself. Um, then this packing efficiency is a good measure. As I said earlier, you can try finding out what's the packing efficiency of these three different arrangements in a cubic unit cell, and would turn out this has the least packing efficiency, followed by a BCC, followed by the FCC, and you can basically calculate these values exactly.